So we now know how to find the Taylor series or Maclaurin series for a given function, and there's a few very special and popular and much needed Taylor or Maclaurin series that we want to kind of go over. One of them we've already seen, which is for e to the x, or our natural exponential function. In this example, we're going to work together to find the Maclaurin series for the function f of x equals sine of x. Remember, the Maclaurin series is just a Taylor series with a being equal to 0. So the big piece we really have to find is, what does the nth derivative of our function look like at x equals 0? So in order to get that process started, let's try to look for a pattern in the derivatives of our function, or the derivatives of our function at x equals 0. So our starting function is sine of x. The first derivative is going to be cosine of x. The second derivative is going to be negative sine of x. The third derivative is going to be, let's see, negative cosine of x. The fourth derivative is going to be back to sine of x. And then we're essentially going to repeat this loop forever. We'll write maybe just one more. The fifth derivative of our function is going to be cosine of x. The sixth derivative would be negative sine. Then we're just going to kind of continue looping around through this cycle. And looking at the kind of pattern in the derivatives here, we can see that we're going to have some repetition in this looping process, but we don't really know what the value is clearly going to be at x equals 0. So we can instead try to look for the pattern in evaluating our function or its derivatives at the center point, in this case for a Maclaurin series, when x is equal to 0. So what is sine of 0? Well, it's equal to 0. What is the first derivative of our function equal to at x equals 0? Or in other words, what is cosine of 0? Well, that's 1. What's our second derivative equal to at 0? Well, that's negative sine of 0, and that's 0 again. Our third derivative is going to be equal to negative 1 at x equals 0. Oops, 0. Our fourth derivative, evaluated at 0, is sine of 0, which is 0. And then our fifth derivative, evaluated at 0, is again cosine of 0, or 1. And so we can see, as we do have a pattern here where every other term is going to be a 0, and then between those terms that are non-zero, we're always going to be alternating between positive 1 and negative 1. So it may be difficult at the moment to see what is the pattern for the general coefficient of our Taylor or Maclaurin series we're working with here. So instead, let's go ahead and list all the terms out and then try to look for the pattern. So remember, our Taylor series, or in this case our Maclaurin series, is going to start by doing the 0th derivative of our function at 0 times x minus a to the power of 0 over 0 factorial. Or in other words, it's going to look like f of 0 times x minus 0 to the power of 0. That's just 1 over 0 factorial. So that's really just f of 0. Then we're going to have f prime of 0 times x to the power of 1 over 1 factorial, plus f double prime of 0 times x squared over 2 factorial, plus f triple prime of 0 times x cubed over 3 factorial. Then we'll write one more, the fourth derivative at 0 times x to the fourth over 4 factorial, and so on. And so plugging in what we know f of 0 is equal to 0. All these terms involving an even derivative are going to be 0. And so it's really only the odd terms that remain or stick around. And well, the first one is just going to be 1, so it'll just be x. The next one is going to be the value of our third derivative at 0 times x cubed over 3 factorial. Well, our third derivative evaluated at 0 is actually negative 1. So instead of adding x cubed over 3 factorial, because that coefficient is really going to be negative 1, it's like we subtract x cubed over 3 factorial. So instead of adding x cubed over 3 factorial, because that coefficient is really going to be negative 1, it's like we subtract x cubed over 3 factorial. Well, the fourth term is going to disappear, so what does the fifth term look like? Well, this coefficient is positive 1, so we'll be adding a 1 times x to the fifth over 5 factorial. The next term that's actually going to show up in our Taylor series or Maclaurin series is going to be that seventh one, and that's going to correspond to negative cosine of x, or a coefficient of -1. So we'll get negative x to the 7th over 7 factorial. Well, the 8th term will disappear because of a coefficient of 0. The 9th term will show up, and it will have a positive coefficient of 1. So that'll look like x to the 9th over 9 factorial. And now we can probably start to see exactly what the pattern is. We have this alternating series of these odd powers of x divided by the corresponding odd factorial. The next one would be negative x to the 11th over 11 factorial, then x to the 13th over 13 factorial, minus x to the 15th over 15 factorial, and so on. And so now we want to try to write this in this sigma or summation notation with a sum going from n equals 0 to infinity. And so the pattern we can notice is we're only having these odd powers show up. The coefficients start off as +1 and then alternate between +1 and -1. So we're going to have -1 raised to some power. And well, if we plug in n equals 0, we want the first one to be positive. If we plug in n equals 1, we want the second one to be negative, and so on. So if we do -1 to the power of n, that will accomplish this, right? -1 to the power of 0 is 1. -1 to the power of 1 is going to be -1. And then we'll get the alternation as desired. So then our powers of x have to correspond to these odd exponents, starting with 1, then going to 3, 5, 7, and 9, all these odd numbers. And we can describe these odd numbers as 2 to the n plus 1, right? Just double checking, the first term corresponds to n equals 0. If we plug in 0, we get 1. That's x to the power of 1. The second term will correspond to n equals 1. If we plug in n equals 1 here, we do get 3. The third term will correspond to n equals 2. If we plug in n equals 2, we'll get x to the 5th, and we'll also get -1 squared, so it's matching up everywhere. And to finish this off, we have to divide it by our exponent, but as a factorial, and that odd exponent is 2n plus 1, so that denominator is going to look like 2n plus 1 factorial. And so the point of this example and exercise was really just to find our Taylor series or Maclaurin series representation for sine of x, and we now have that. We'll look at it later on, but it turns out that this power series representation for sine of x is also going to have an interval of convergence of all real numbers, or from -infinity to +infinity. The other kind of interesting property that our power series or Taylor series or Maclaurin series representation preserves that I always like to point out is a little bit easier to see in this expanded form. Notice how all the powers of x that stick around in our series are these odd powers of x. Another property of our sine function that we talked about way back in like trigonometry is the symmetry of our sine function, right? The type of symmetry we look for in a function is whether it's an even function or an odd function. Even functions are graphically split exactly down the middle by the y-axis or mirrored across the y-axis, and our odd functions have that graphical symmetry of being rotations by 180 degrees about the origin, or a horizontal reflection is equivalent to a vertical reflection. Another really cool property of even and odd functions, which is where I personally like to think the name of an even and odd function comes from, is in their power series, Taylor series, or Maclaurin series representation. If we look at an odd function like our sine function here, notice how all the powers involved in the series representation are odd powers. And that's going to be true for any series representation we look at for an odd function. They all include the odd powers. And if we look at the Maclaurin or power series or Taylor series representation for an even function, it will have no odd powers of x. It will only have even powers of x.